All right. So this is going to be Physics 111, Chapter 11, which is going to be rolling, torque, and your angular momentum. So let me go ahead. All right, let me open up a new page right now. So supposedly, let's say I have a ruler. Now, if you apply a force, let's say this ruler is pivoted at the center of mass. If you apply a force on this side, what's going to happen to the ruler? Well, it's going to rotate on that side. What would happen if you apply a force on the other side going this way? Well, if you have a force going on this side, that means you're going to have, it's going to rotate the other way. So this is your ruler, and these are your force applied. Now, what causes this object to turn? That's when we talk about torque. Is what causes an object to have angular acceleration. Now your torque is going to be your force multiplied by the distance to that pivot point that you want. So it's Newton multiplied by your meter, which is going to be Newton meters. So let's say this is our little ruler right over here, and we have the pivot of the point pivoted right over here. Now, you got, let's say we got a force of 5 newtons at a distance of 10 meters coming in there. And from a distance to the end, 5 meters, we get another force that we're trying to apply that's gonna keep this in equilibrium. Now, when we talk about torque, it's very important to remember 2 things. When your torque, well, let me just rewrite this in a different color. So when you go counterclockwise, your torque is positive. When you go clockwise, your torque is negative. Now, in order for us to see if this is in equilibrium, that means we have to look at, that means all the forces applied on it has to equal to 0. When we're talking about all the forces, we're talking about all the summation of all the forces in the x direction has to equal to 0, and summation of all the forces in the y direction has to equal to 0. So taking our example over here, for the first point, our torque is going to equal to, now this is going to go in the counterclockwise direction. That means your torque is going to be positive. So it'd be your force multiplied by your distance, which is 5 multiplied by 10. So it's 50 Newton meters. Now for the second one, you are going counterclockwise. So your torque is going to be negative. So it'll be negative. The distance is 5 multiplied by F2. Now we mentioned the fact that all the forces has to equal to 0 in order for it to be equilibrium. We also need to mention that all the torque forces is going to have to equal to 0 when you have equilibrium. That means all your torque is going to equal to 0. That means your torque 1 plus torque 2 in our example has to equal to 0. Which means T1 is 5 times 10 minus 5. F2 is going to equal to 0. That means F2 is going to equal to minus 50 divided by 5. So it's going to be 10 newtons. So really, for this one, it's going to be minus 5 multiplied by 10. So your torque is minus 50 newtons on this one, which makes sense because it opposes the 50 newton that you have. Excellent. So let's take a look at this. According to Newton's second law, a net force causes an object to have an acceleration. Now, what causes an object to have angular acceleration? That's when we actually talk about torque. So the magnitude of torque is going to equal to the magnitude of the force multiplied by the distance to that pivot point, to the axis of rotation. That means your torque is going to equal your force multiplied. We had it as D, your book has it as L. So force multiplied by the distance, which is going to be Newton times meter, so it's Newton meter. Now, in order for it to be in equilibrium, that means all your forces has to equal to zero. That means all your forces in the x direction has to equal to zero, which means you don't have any acceleration in the x direction. All your forces in the y direction is going to have to equal to zero. That means all the acceleration in the y direction equal to zero. Same thing when you have a zero angular acceleration, that means all your torque force equal to zero. So going back to our example, if we actually look at the forces at the if we look at the forces at the y direction, what you're going to have, your sigma Fy is going to equal to zero. That means all your forces in the y direction, which is going to be your 5, and then you got minus 5. So your 5, this is going to be your F1. Let's call it, this is F1, yeah. Your F1 is positive because it's going in the positive x direction, plus F2 equal to 0. Now, in this case, F1, let me just put F2 in parentheses. F1 is positive. F2 is positive. That means your sigma torque is going to be 50 minus 50, which is 0, which is that's what we need. And we don't have any forces on the x direction going in. So your forces in the x direction is going to be 0. Now, so a rigid body is in equilibrium if it has 0 transitional speed and a 0 angular acceleration. In equilibrium, the sum of the externally applied forces is 0, and the sum of externally applied forces is 0. So let's take a look at this question. You got a woman whose weight is 530 newtons. Is poised at the right of the diving board with length 3.9 meters. The board has negligible weight and is supported by a fallocrium of 1.4 meters away from the left end. Find the forces that the bolt and the fallocrium exert on the board. Now, obviously the bolt stays on the ground. So, and you got the woman. So the woman is exerting a weight going down there, fallocrium going up, and your bolt is actually pulling it down, which the distance between the fallocrium and the rotation of the axis is 1.4, and the whole board is 3.9. So let's go ahead. They call it LW. So let's go ahead and do this. So let me come in. You got a woman whose weight is 530 newtons. So here she is right over here. She got a weight of 530 newtons. You got your fallocrium and you got your bolt right over here. Your fallocrium is taking a force going that way, and this one is taking a force this way. Let's call this one F1. Let's call this F2. The distance, they have it called as, I'm just going to keep it as the book, is LW. The distance from the person jumping to the bolt. Now, the distance between the fallocrium and the bolt is 1.4 meters. Wonderful. So your LW, let me just write this down, is 3.9 meters, and they call this L2, so I'm going to call it L2. So this is 3.9 meters, and your L2 is 1.4 meters. That means if you look at all the forces for the torque, which is going to have to equal to 0, that will be in equilibrium. What you're going to have? You're going to have the torque is going to equal to, the first one is this one, that's going clockwise. So it's going to be negative your weight multiplied by LW, plus you got the F2. F2 is going to be, here's that, so this is going this way. So that means this is going to be counterclockwise. So it'll be F2 multiplied by your 1.4 plus F1, which is this one multiplied by your distance 0. So again, this is going to go to 0. That means your torque is going to equal to minus W, LW, plus, and this, oh, by the way, this all has to equal to 0. So plus F2 times 1.4 is going to equal to 0. That means F2 is going to equal to your weight multiplied by LW divided by your L2, which is 1.4. So it's 530 multiplied by 3.9 divided by 1.4. Let me plug it in. I got 1,480 newtons. That's for your torque. Now let's look at all the forces summation in the y direction. What you're gonna have? Well, if you actually look at it, what you're gonna have? You're gonna have minus F1 is going down, plus F2 minus your work is gonna equal to 0. We already defined F2 as 1480. So this is gonna equal to minus F1 plus 1480 minus 530 is going to equal to 0. That means your F2, F1 is going to equal to your 1480 minus 530, which equals to 950 newtons. You can look at all the forces in the x direction also, which is going to have to equal to 0, which in this case, we don't have any forces in the x direction. Everything is going in the y direction. So all the force in the x direction is 0. So it's in total equilibrium. Now let's see. Yeah, and it's correct. We got 1480, which is divide that, subtract that 530, so you get 950 newtons for F1. So F1 is 1480, F2 is 950. Let's do another example, shall we? You got the arm is horizontal and weighs 31 newtons. The dial muscle can supply 1,840 newtons of force. What is the weight of the heaviest dumbbell he can hold? All right, well, let's go ahead and write this down. So you got W, so you got your weight of the dumbbell, your weight of the arm, which is going to be right over here from the middle, and you got your rotational axis, which is your shoulder. So let's go ahead and get a new page. So here's our little arm, I would say. So you got WD, the weight of the dumbbell going on here. And you got the weight of the arm. And you have is going towards the muscle M on this one. Now, so if this is, I'm gonna write this in blue. If this is the distance LM, I'm just gonna call it LM. Okay. That means you got an angle over here. So here's your LM, the movement that's going in with the torque. Now again, your pivot point is over here. Let me just get a little thinner. So this is gonna be your LA, and this is gonna, the whole thing from over here to the end, that's gonna be your LD. So your weight of the arm is 31 newtons. Your mass is 18, your M force, this M force over here, I'm gonna give it big M. M force is 1840 newtons. Your distance from the arm to the shoulder is 0.28 meters. Your distance from the dumbbell to your shoulder is 0.62 meters. And the distance for M, I'm gonna call it big M, 1.15 meters. So we got everything in, and we are looking for your weight of the dumbbell. So let's look at all the torque forces in order for it to keep it equilibrium, which is gonna have to equal to 0. Let me just rewrite this down. So looking at all the torque forces, what do we have? We have minus, this is going counterclockwise, so we're minus WD multiplied by LD minus your work for the arm multiplied by length of the arm. And this one is going clockwise, so this, counterclockwise. So this is gonna be plus big M multiplied by the length, big M force. I don't know what they call M, but M force multiplied by the length for M is gonna have to equal to 0. Now let's substitute the numbers for it. So this is gonna be minus WD multiplied by 0.62 minus 31 multiplied by 0.28 plus 1840 multiplied. Now, you got 1840, and then you got your distance going from here to here is 0.15. Multiplied by, now this, what you're gonna have? You're gonna have a vector with the coordinates of fx and fy. Now, this is going to be 13 degrees. Having to find the angle, so you're going to be moving 13 degrees. So you're going to go sine, which is sine the angle of the 13 multiplied by your 0.15. This is going to be, let me just rewrite this down. 13. We have a 13 angle, 13 degrees angle. So it'll be sine 13 degrees angle, because that's what we're trying to achieve. Sine 13 this. So that will make it minus WD multiplied by 0.62 minus 8.68 for this one, plus plug in the number, sine 13, plus 0.15, multiplied by 1840, so it'll be 62.087 is going to equal to 0. That means your work is going to be 50, so these two is going to be 53.407 divided by 0.62. So it's going to be 86.14 in newtons. Now, looking at, let me get a different color. Let's look at all the different Y forces. So what you're going to have, you would have your WD, your WA, and then you got M going into the Y, it'd be sine theta. So this is going to equal to minus WD minus WA plus M sine theta. And again, it's on top with the y-axis. It's going to have to equal to 0. Now, if you look at the x direction, The only thing that you have x, so this doesn't have an x. Doesn't have an x. The only one that this one has in the x direction is this one. So this is going to be 13 cosine theta. So it would be your m cosine theta. Okay, so that's your forces in the x direction, which is m in the x direction. This is going to be your m in your y direction. So let's go ahead. Your tau equals minus work for the arm multiplied by the distance for the arm minus the work for the dumbbell multiplied by the distance for the dumbbell plus the M force that you got over here, which is they have it as muscle. So your muscle force multiplied by your distance for the muscle, which in this case is going to be 0.15, the distance multiplied, we want this one. So it's sine the angle. Okay? So be sine the angle. And again, if you think of it this way, right? Let me just pull this up a little bit. If you think of it this way, let me just write it on the side. So M, so you got sine theta is your opposite over hypotenuse. That means your opposite, the one we were trying to find, is your sine theta multiplied by your hypotenuse, which is in this case, this is our big M. So this would be M sine theta. Same thing for the cosine. When we actually talk about cosine theta, again, it's the adjacent over hypotenuse. So that means the adjacent that we're looking at, if we want to find it, is your cosine theta multiplied by hypotenuse. Excellent. So plug it in, you should get 86.1. That what we just got, newtons. Now, we talked about center of gravity. So let's define the center of gravity. The center of gravity of a rigid body is a point at which its weight can be considered to act when the torque due to the weight being calculated. So basically, when an object has a symmetrical shape and its weight is distributed uniformly, the center of gravity lies in the geometrical center. Now, the center of gravity is going to equal to your x1 multiplied your weight multiplied by the distance, weight 1 multiplied by x1, plus your second weight multiplied by the distance, plus your third weight multiplied by the distance, etc., divided by weight 1, weight 2, plus weight 3. So let's say if we have an example. If we have an arm that has 17 Newton, 11 newtons, and the hand has 4.2 newtons. Find the center of gravity for the arm. So basically, you got the 17 newtons, multiply that by your 0.3. You get your 11 newtons, multiply that by 0.38. Then you get your 4.2, which is multiplied by 0.61, divided by 17 plus 11 plus 4.2. So your answer is 0.28. Awesome. Now, when you have an object going in a circle, so let's say, and we talked about this briefly from the last chapter. You got, so this is your pivot point, this is your radius R, and you got, I don't know, some kind of object that's going this way. Now, that object is going to have a force that's going to be your tangential force. And it is defined as your mass multiplied by your tangential acceleration. You see, because that object is going in a circle, it's going to have a tangential acceleration, and it's going to have a tangential velocity. So your Ft, your tangential force, let me just write this down, is mass times your acceleration tangential. So your AT, by the way, if you remember, tangential acceleration is going to equal to R alpha. And again, alpha is your angular acceleration. Tangential acceleration, that's tangential acceleration. And R is your radius. And let me just write down M for mass. Now, so when we're talking about torque, we're talking about your force multiplied by distance. In this case, is your tangential force multiplied by the distance, which is the distance in this case is your R. So your torque, let me just write this down. Is going to equal your tangential force multiplied by the radius. That means your tangential force is going to equal to the torque divided by the radius, which is going to equal to your mass multiplied by R multiplied by alpha. And again, let me just, this is your mass over here. Again, this is your radius. And alpha is your angular acceleration. So your torque really is going to equal mR square alpha. Now your mR square, that's what we defined, the wrong color. Your mR square, that's what we define as your moment of inertia. Let me just write this down better. So your torque, actually, the sigma for torque is going to equal to your sigma of mR square alpha. Particular, it'd be, and again, this is I, so it'd be the sigma of I alpha. And again, your I is going to equal to all summation of your mass multiplied by your distance squared. Okay. So your tangential force is going to equal to your mass multiplied by your tangential acceleration. Your torque is going to equal your tangential force multiplied by the radius. Your tangential acceleration is R alpha. Your radius multiplied by the angular acceleration. That means your torque is going to equal to mR squared multiplied by alpha. And again, mR squared, that's your moment of inertia. So for rotational analog of Newton's second law for a rigid body rotating about a fixed axis, your net external force torque is going to equal to the moment of inertia multiplied by your angular acceleration. And again, your moment of inertia is going to equal to all summations of m, your mass multiplied by your radius squared. So let's say we have a question. All right, so you got two particles, each have a mass m, and are fixed at the ends of a thin, rigid rod. The length of the rod is L. Find the moment of inertia when the object rotates relative to an axis that is perpendicular to the rod at one end and half, and the center, which is going to be half. So this one is going to be a full one. This one is going to be half, R1, R2. That's the full rod. So let me go ahead and open up a new page. So for the first one, part A, let me just go ahead and draw this. Oh, that's ugly. That's better. You got a rod, and you got a rod over here, so that's M1, M2, and we're gonna call this R2. I'm just gonna call it like this one, R2. So that means your moment of inertia equals your summation of all your masses multiplied by R squared, by R squared, which is gonna equal to your M1 R1 squared plus M2 R2 squared. Well, R1 is going to be 0 squared plus M2 R2 squared. So this little fella right over here is going to go to 0, which means that your moment of inertia is going to equal to M2 R2 squared. And we said that the length equals to R. So we said R equals to L. That means I equals M2L squared. Okay, part B. Part B stated that the rod right now is halfway between both points. So this is going to be your R1, this is going to be your R2. Again, this is your mass 1, in the end, this is your mass 2. You get a different color. That means your moment of inertia, let me just write this down under it, is going to be your summation of mr squared, which is m1 r1 squared plus m2 r2 squared. Well, if you look at the first one, again, in this case, r is going to equal to L over 2. That means now in first case, it'd be m1 multiplied by L over 2 squared plus m2 L over 2 squared. Now, both particles, they have the same mass m. That means your m1 is going to equal to m2, which is going to equal, we're going to call them m. So, solving for this, what you're going to have? You're going to have m1 L squared over 4 plus m2 L squared over 4, which is going to equal to m L squared over 4 plus m L squared over 4, which is going to be 2m L squared over 4, which the 2 and the 4 disappear, so this becomes 2, this becomes a 1. So this is going to equal to m L squared over 2. So your moment of inertia I, is going to equal to m L squared over 2. Let's look if we have the right answer. So again, your I equals your summation of all your mass multiplied by your radiuses. So M1 R1 squared plus M2 R2 squared. R1 is 0 because, again, we're rotating around the middle axis. So this one is going to equal to M2 R2 squared, which R is going to equal to L. So it'd be ML squared for the first one. For the second one, your R equals L over 2. So if this whole thing is L, this is L over 2, and this is going to be L over 2. That means your moment of inertia is going to equal to M1 R1 squared plus M2 R2 squared, which is going to equal to ML over 2 squared plus ML over 2 squared. And again, both methods are the same. So you're going to end up getting your moment of inertia as 1/2 ML squared. Awesome. Now, let's say so we talked about how the torque is going to equal, which we just did, low mr squared multiplied by alpha. Now, your mr squared, that's your I, moment of inertia. That means your summation of all the torque equals your summation of mr squared multiplied by alpha, which is going to equal to I alpha. So your torque is going to equal to I alpha. Now, supposedly we get a pulley. So this is a pulley. And I don't know, I'm just going to use green for the rope. So you get a rope going in, and that's your R over here, and it's rotating this way, right? You're pulling F on this side. So that's a rope, that's your pulley, and it's rotating with an angle theta. Now, your work that we have is what? It's going to be force multiplied by the distance. And in precise, as your force, your distance is going to be your arctan that you're going, S. So, but S, we defined it before as R theta. That means that the work is going to equal to FR theta. But F multiplied by R, that's force multiplied by your distance, which means this is going to be your torque. So this is actually equals to your torque multiplied by your theta. So your work equals your torque multiplied by the angle theta. And now the angle must be in radians. And your work is in joules. Now, this little work, we're going to give it R for rotational work. Now, when you actually do work, let's say you have, I don't know, a lever arm, and you're actually turning it in this way. So you're going to have kinetic energy. So your kinetic energy, in this case, is 1/2 mv squared. In precise, it is the tangent velocity, right? Now, because it's a tangential velocity, that means that is your tangential velocity. Vt is going to equal to r omega. And again, omega, that's your angular velocity. So your tangential velocity is your r omega. So that means your kinetic energy is going to equal to 1/2 m r square omega square. But if you notice, you get mr squared, which is again your I, your moment of inertia. That means this is going to equal to 1/2 I omega squared. That means your kinetic energy is going to equal to 1/2 I omega squared. And this is, ladies and gentlemen, that's your rotational kinetic energy of a rigid rotating object. You see, if you have a mass that actually has a velocity v, is going to have momentum, right? Which is your mass multiplied by your velocity. Now you take that mass and you pivot it on a point, let's say with a nail. That's your mass, that's going to be your r. And that's where we define the angular momentum. So how much, the question is, how much momentum something has? See, here's the thing, right? So let's say you got a truck coming towards you versus a car, right? Let's say a big or 18-wheeler versus, I don't know, a coupe. Which one has more momentum? Well, obviously the one with the big truck, because it has a bigger mass. That means it's harder to stop. So the more momentum you have, the harder to stop. Now, to change momentum, you have to apply a force. For an amount of time. So to change your momentum, you need to apply a force in a certain amount of time. Now, and that's what we call, ladies and gentlemen, your impulse. It's a P, impulse, which we give it the letter J. Now, your angular momentum, we give it the letter L. And the reason that we give it the letter L, because the best explanation I got was because they ran out of letters for the physics variables and decided that's the only one they have left and decided to give it to angular momentum. Now your angular momentum is going to equal to your mass multiplied by your tangential velocity multiplied by your r, your radius. And again, the tangential velocity is your magnitude of velocity perpendicular to the radius. which means, okay, so, well, before I said which means, now, remember that we got tangential velocity, right? Now, the tangential velocity is what's going to equal to. That's your VT is going to equal to your omega r. That means your tangential velocity equals, not tangential velocity, yeah, tangential velocity, hold up. That means your angular acceleration velocity equals to tangential velocity divided by r. That means your L equals m omega r squared. Well, let me just write this down. M omega r, which is L omega r squared. Not L, M. Now, your L, your R multiplied by M, again, that's your I. So this is going to equals to I omega. So your angular momentum, L, is going to equal to your moment of inertia multiplied by your angular velocity, which is, if you actually apply the formula, you got what? R, and you got your velocity, and you got your angular velocity. So that means when your R goes up, that means your velocity goes down, which means if the velocity goes down, that means your angular velocity goes down. If your radius goes down, that means your velocity goes up. That means your angular velocity goes up. Think of it as your ice skate figure skaters, right? When they're actually figure skating and they're turning around fast, they put their hands together inside their body so they can have a faster movement. That way they would have a lesser radius. When they extend their arm out, they have a bigger radius, so they actually slow down. Your velocity goes down. Now, so let's look over here. So when you're actually dealing with a rotational object, your work is your force multiplied by your distance, which is your work is your force multiplied by your distance, which is going to be F multiplied by S. S is going to be arc tan, which is going to be R theta. So, and your torque is equals to FR. So that means your work is your torque multiplied by theta. It's how much torque you're putting in multiplied by the angle that you're turning it in by. So, and that would be your rotational work. So the rotational work done by constant torque in turning an object through an angle is your tau multiplied by your theta. Here. All right, now the work is going to be, again, because work is going to be in joules. Now, again, when you have a rigid body, that means you have your kinetic energy, which your kinetic energy is going to be 1/2 mv squared, which is, in this case, is your tangential velocity squared. So it would be 1/2 m, and we define the tangential velocity as r omega. So it would be 1/2 mr squared omega squared. But mr, again, we said that's your mr squared, that's your moment of inertia. So this is going to equal to, your kinetic energy equals 1/2 omega I omega squared. So your rotational kinetic energy of a rigid rotating object is 1/2 I omega squared. Now the angular speed must be expressed as radius per second. So let's do this little example, shall we? You get a thin-walled hollow cylinder and a solid cylinder. Start from rest, the top of the incline is going down. Determine which cylinder has the greatest transitional speed upon reaching the bottom. When you reach the bottom, that means your height is 0. Your initial height is whatever it is, and you go to 0. Now, the energy, let me just do this, and this was example 13. Now your energy is going to be, so it's going down. So you got basically this, and you got an incline, and you got, well, let me just redraw this. Here, that's better. You know, that's going down. Now, when that thing is going down, you're going to have 3 different energies. You're going to have a kinetic energy that's moving in, right? You're going to have a kinetic energy. You're going to have a rotational energy. And you're going to have gravitational potential energy. Your kinetic energy is 1/2 mv squared. Your rotational is 1/2 I omega squared. Next time you rewrite the omega, that way you would not think it's W, I omega squared, and these are 1/2, plus your gravitational is mgh. So your energy before is going to equal to the energy after. So before, what you're going to have? You're going to have 1/2 mvi squared plus 1/2 I omega I squared plus mgh initial, not squared. Now remember, your distance over here, that's your h initial. Your distance right over here, that's your h final, which is going to be 0 basically. Now after it goes down, same thing, you're going to have a kinetic energy, which is going to be 1/2 mvf squared plus 1/2 I omega final squared plus mghf. So basically we said the initial height, the final height is 0. So this thing is going to go to 0. And what else? When it goes down, when you start, your initial velocity is going to be 0. So let me just write this down. Vi is going to equal to 0. This is going to be hf is going to equal to 0, which means your rotational is going to equal to 0. Your angular speed is going to equal to 0, so it's going to go to 0. So what do you have left? You get 1/2, let me just get back to red. mv final square plus 1/2 omega I final square is going to equal mghi. Now in the question, we're trying to find the final velocity. See which one's going to get there first. I mean, the one that's faster is going to get the final velocity. So how can we get the velocity? Well, let me just change colors. Your omega square is going to equal to your velocity divided by your radius. That means, let me go back to red, put this, 1/2 mv final square plus 1/2 I, and instead of your omega, we're going to put your v, which is going to be your final velocity divided by your radius square. This is squared, so this is going to be squared, this is going to be squared. It's going to equal to mghi. That means your final velocity is going to equal to your 2mgh naught divided by m plus I over r squared. Now, if the momentum was close to the radius in value, that means, well, let me start. If your momentum was way smaller than the radius, that means this thing is going to go to 0. So that means you're going to have a higher speed. If this one goes closer to r or higher, that means this thing is going to go to less. So if I was small, what you gonna have? Bigger VF. And then the same thing. If I was, I don't know why I have an extra S. Big, that means smaller final velocity. So you just put in the masses and the initial moment of inertia for those, and you find out which one goes in. So basically, your energy before is going to equal to your energy after. Your energy is going to consist of 3, which is your kinetic, your rotational, and your gravitational. So 1/2 mvf squared plus 1/2 I omega f squared plus mghf is going to equal to 1/2 mvi squared plus 1/2 I omega I squared plus mghi. So again, an omega equals to vf over r. Solving for the final velocity, you get 2 mgh naught over m plus 1 I over r squared. So we define the angular momentum. The angular momentum L of the body of rotating about a fixed axis is the product of the body's momentum of inertia, moment for inertia, and its angular velocity with respect to that axis. So L equals I omega. Okay, now your angular momentum is going to be in kilogram meter square per second. Your angular speed is going to be in radius per second. And this is basically the example we talked about. When you have an ice skater turning in fast, her arms are inside. When she actually puts her arms up, her speed slows down. All right, well, let's take another look at another example, shall we? All right, so actually, before we do this, I need to explain something. Let me go ahead and explain something first. I just noticed. Now, we said that change in kinetic energy is, actually, let me get black. We said that the change in kinetic energy, again, is your kinetic energy final minus your kinetic energy initial, which is 1/2 mvf square final minus 1/2 mv initial square, which is your work. Now, your work is defined as your integration from initial x to final x f dx, your force multiplied by your distance. And your power, which we talked about, which is going to be just regular P, is dW over dt, which is going to equal to F multiplied by V. So your delta K, your change in kinetic energy, which is your final kinetic energy minus your initial kinetic energy. When you talk about rotation, okay, and that's what we just did earlier, right? We just substituted, we substituted the tangential velocity with where's my initial? Here it is. I omega. Right, tangential velocity is omega, your angular acceleration multiplied by your radius. So, and it's going to equal to I omega. So your kinetic energy is going to equal to 1/2 I omega final square minus 1/2 I omega initial square. And again, that equals to your work. And let me just write this down. Angular velocity that means your work is going to actually equals to your initial theta to your final theta. Actually, let me get a different color on this. Let me get blue. That means your work equals your integration from initial theta to your final theta, tau d theta, which means that the work is going to equal tau to theta final minus theta initial. That means your power, which is your dW over dt, is going to equal to your torque multiplied by your work. Now, change on this. Now, your kinetic energy, get my notes 1 second. Now, again, your kinetic energy, which is your final minus kinetic energy initial. And we said that kinetic energy is actually 1/2 mv squared, and your v is omega r. That means your delta k E, your change in kinetic energy, equals 1/2 mr squared omega final squared minus 1/2 mr squared omega initial squared. And again, we have m and r squared, which is going to be your momentum. And here it is also. Now, all of this, again, is going to equal to what? To your work. So your change in kinetic energy is 1/2, again, I omega final squared minus 1/2 I omega initial squared. Now we said the change in work equals your tangential, your force, mainly the tangential force, r d theta. But, and a big but, we said that the torque is your tangential force multiplied by r. That means your dW equals your tau d theta. And we said that means your work equals your integration again. Let me just line down work. From theta I to theta F tau d theta. That means your work is going to equal to your tau, your torque multiplied by your theta F minus your theta I. And again, your power is your dW over dt, which you need to integrate this with respect to t. So you get tau d theta over dt. And your t theta over dt, that's your omega. So your power is going to equal to your torque multiplied by omega. Now, let's say you have a wheel going down. Here's the floor over here. Actually, let me just make this. Hold on. That's better. So it's rolling down this way, right? And you get the acceleration of center of mass, and you get a point B, and you get the point B in a different color. That's your point B. And you got, because it's rolling that way, that means your friction force is going this way. So your kinetic energy, which is going to be what? 1/2 I omega squared. Again, let me just write this down. This is angular. I don't want you to confuse this and the work. So that's angular speed, and that's rotational inertia. Inertia of the wheel at point B. That means your inertia at point B is going to equal to your center of mass inertia multiplied by your mr squared. Let me just go down. mr squared. So that means your kinetic energy. So this is, oh, hold up, I forgot to add the P. So this is IP. In inertia at point B. So that means your kinetic energy is going to equal 1/2 I center of mass omega squared plus (1/2) mr squared multiplied by omega squared. And again, R is the radius. Actually, I'll use big R, so I'm just going to use radius. Okay, so you get the radius on here. Actually, let me just write this down way a little better. Radius. And this is omega. That way you can actually see it. But the phi center of mass equals omega r. I forgot to square over here. So basically, this little fella over here, you can substitute it for this side. So your kinetic energy is going to equal to 1/2 I center of mass omega squared plus 1/2 multiplied by your mass and multiplied by your velocity of the center of mass. You see, if no, let's say you're rolling down a hill, right? So let's say this is your ball, you're rolling down this way, right? So let me get this. All right, so you're gonna have an FG going down, force multiplied by gravity, your gravitational force. You got your neutral force going up there. And if this is going on here, this is gonna be your theta, right? And you're going this way. So that's gonna be your FG sine theta. And of course, your Fs, your friction, is going the other side. So if this is Fg sine theta, let me get a different color. That means this one over here is Fg cosine theta. You see, again, this is a convolution between both the lines, where this is your theta over here. So your net force, which is what? Your mass times acceleration, right? And your torque net is your I alpha. Now looking at that picture, what you got? You get your Fs, your frictional constant, minus mg sine theta, going the other side is going to equal to your ma center of mass. Now, your T net, your net torque, is going to equal to your center of mass momentum multiplied by alpha, which is your radius multiplied by your coefficient of friction. That means your coefficient of friction is going to equal to I center of mass alpha divided by R. And the center of mass acceleration, again, is going to equal to alpha R, same thing. So that means your alpha is going to equal to center of mass acceleration divided by R, which is going in the opposite side. So it'd be minus a center of COM. Let me just write this down. Center of mass divided by R. You see, alpha is counterclockwise. That means your center of mass is going to be negative. Because it's in the negative direction of x-axis. So basically you got, let me get the red on here, your net torque, that's what it's going to equal to. And from this one, your Fs is going to equal to minus I center of mass, A center of mass divided by your mass. No mass, I'm sorry, R2, R squared. I don't know where I got center of mass from. R squared. That means your acceleration for center of mass is going to equal to minus g sine theta divided by 1 plus the moment of inertia for the center of mass divided by mr squared. Now, when we talk about torque, we're talking about force multiplied by distance. Which most of the cases would be r for the radius, right? But then if you notice in the first question that we had, we actually used sine theta. Where's the question that we had? Yeah, this question, we had sine theta used for the torque. So really, what we're saying, the torque is going to equal to Fr sine theta, which if you remember, this is going to be your cross product. So your torque is going to equal to your R multiplied by theta, R cross theta. Now again, on perpendicular angles, your sine theta is going to equal to 1. That means your torque, again, is going to equal to RF, and that's what we've been doing. Now your angular momentum, L, is going to be your R cross your momentum, which, let me just do this. Your momentum is M multiplied by V. So your L equals to R cross mv. Your mass is the same everywhere, so it comes out, so it'll be R cross V. So your dl over dt is going to equal to m R cross dv over dt plus dr over dt. Sorry, dr over dt multiplied by v. So r dv dt plus dr over dt multiplied by v, your velocity. So your dl over dt is going to equal to m. Now, dv over dt, that's going to be what? What's your velocity over your time? That's your acceleration. And what is distance over time? That's your velocity. That means dl over dt equals m r cross a on this one plus v cross v. Well, anything that crosses each other the same is going to equal to 0. So your dl over dt is going to be m r cross a and if you actually multiply it inside, what you're going to have? R cross ma. Well, ma from Newton's second law, that's F. F equals ma. That means your dl over your dt is going to equal to R cross F, which is your summation of all the R's cross F's, which is, again, this is going to be your torque. So that means, I'm just going to write this in this big down, your torque is going to equal dl over your dt. Now, one thing I need to mention about the angular momentum. Again, let me just write this down. Angular momentum. What you're going to have is going to be R. Again, we said this R cross MV, which is M R cross V. And R cross V, again, we defined it before as RV sine theta. Now, and let me just get black on this. For 90 degrees, sine theta is going to equal to 1. That means L equals MRV, which is again kilograms meter squared per second, which is the unit for angular momentum. So your angular momentum is going to equal to your first angular momentum plus your second one plus your third one plus whatever it is to ln plus ln. So it is your summation from I equals 1 to n to ln. And your dl over dt, we said, that means your dl over dt is going to be equal to summation from I equals 1 to n dl, or you can do dln if you want to, all the l's divided by dt. I'm just going to keep it without the l, that would be easier. Now L over T, that's your torque. That means your dl over your dt is going to equal to your summation from I equals 1 to n to all the torques. That means your torque is going to equal to dl, you change momentum, over your change momentum divided by change of time, dl over dt. That means your dl equals your torque dt. And again, your L, said L equals MRV. Actually, let me write it down over here again one more time. Yeah, here it is. So your L equals MRV, right? So let me get this out. So your L equals MRV, and that's what we just did. Mass multiplied by radius multiplied by velocity. And it's a summation from I equals 1 to n Li. So it's a summation of MRV. And V, we said is R omega. That means your angular momentum equals the summation of MR omega R, which is, again, this is omega. Your omega summation of MR square, which again, MR square, that's your I, that means your momentum, your angular momentum equals I omega. So looking back over here, let's do this question real fast. An artificial satellite is placed in an elliptical orbit about this Earth. It's pointing closer to the approach. So a bogey is when the planet or the satellite is far away from the Earth. When it's close away to the Earth, it's called a perigee. Okay. So what do we have? We have the 8.37. Which is the distance to the perigee. And the distance for the bogey, the furthest is 25.1 times 10 to the 6. Let me just do this. Okay. So your R perigee, we said it was 8.37 times 10 to the 6 meters. And your distance for that bogey is 25.1 times 10 to the 6 meters. And we have a speed satellite of 8450. So VP is 8450. Now we said that your angular momentum equals I omega. That means your angular momentum for the bogey equals the angular momentum for the perigee. For the bogey, what you're going to have? You're going to have, well, let me just write this down first before. This is going to be I omega for the bogey equals I omega for the perigee. Now your I, let me get the red color, is mr squared, and your velocity, your angular velocity is v, well, it's really vt over r. That means your m ra squared, again, we're doing for a, va over ra is going to equal m rp squared vp over rp. That means your m va over ra equals m vp. Well, hold up. Actually, the m's cancel out. Let me cancel them out first. That means your masses cancel out. And when the radius cancel out. So what do we have left? That means your m, r, a, r, not m. We canceled m out. I'm sorry. r, a, v, a is going to equal r, p, v, p. That means your VA equals RP VP over RA. Now let's plug in the numbers. RP is 8.37 times 10 to the 6th power multiplied by 8450 divided by your 25.1 times 10 to the 6th power. Let me plug this in the calculator. 50 divided by 25.1. I got 2820 meters, almost 2820 meters per second. Let's check. So your angular momentum equals I omega. I, the moment of inertia is mr squared. Omega, that's your angular velocity, which is v over r. So mr squared va over ra equals mr squared vp over rp. Awesome. So again, we talked about the arc time, which is your S equals theta r, and your center of mass equals omega r. Now, if you combine the rotational and your transitional kinetic energy, you get, which we went to in deep, getting the equation is 1/2 I center of mass multiplied by omega squared plus 1/2 m v center mass squared. Again, your A center mass is alpha r, and we obtain the equation for the center of mass for minus g sine theta over 1 plus I center of mass divided by mr squared. Here's a question that you can actually do that on your own. So the general equation for the torque is tau equals R cross F, because it's going to be RF sine theta. Again, on a perpendicular, sine theta is going to equal to 1. So using a perpendicular component of force, tau equals RF, because sine theta is going to equal to 1, which means that the angular momentum, which is your distance multiplied by your momentum, is going to equal to mr cross v. which we saw it's going to be RMV sine theta. And we actually looked at, we wrote Newton's second law as the net torque equals dL over dt. And we got to F equals your change in momentum divided by time, power divided by time. So your angular momentum of a rigid body is dL over dt. So your torque is equals to dL over dt, which equals to mr, omega multiplied by mr squared. And that should conclude chapter 11 for physics 111. If you have any questions, just email me or call me or text me at 256-348-1480. Thank you.